Hello, my name is Allison Wing, and today we'll talk about some of my recent work on clouds and convective self-aggregation in a multi-model ensemble of radiative convective equilibrium simulation. First, I'd like to acknowledge the contributions of my graduate student, Catherine Stoffer, and Tobias Becker, who led part of this work, in addition to the many other contributors to RCEMIP, totaling more than 40 authors. Radiative convective equilibrium is a statistical equilibrium in which there's a balance between the net radiative cooling of the atmosphere and convective heating. As such, it is a time-honored idealization for understanding the tropical atmosphere and its sensitivity to relevant forcings. RCE remains the simplest possible way to phrase many questions about climate, including questions about responses of clouds to warming, for example. Despite its simplicity, many questions remain about the basic physics of RCE, and one phenomena that has arose in recent years is the self-aggregation of convection, in which convection spontaneously organizes through radiative convective feedbacks. Now, these questions of self-aggregation, in particular, how it might affect climate and how clouds and convection change in response to warming, have been investigated before. But previous studies have differed in many ways, making it difficult to assess whether the diverse results are a real reflection of model uncertainty or artifacts of the experimental design or diagnostics used. And so this motivated us to do a coordinated intercomparison of radioconvective equilibrium called RCEMIP. And RCEMIP allows us to investigate these questions as well as assess the robustness of the RCA state across a much wider spectrum of models than had previously been used to simulate it. Another advantage of RCE is that it's accessible by many different types of models. And so RCEMIP includes participation from more than 30 models, including models with parameterized convection like GCMs and single column models, and models with explicit convection like cloud resolving models, LES models, and global cloud resolving models. We simulate RCE as an aquaplanet with uniform insolation and SST, no rotation, and where convection is just initialized from random noise. We have two different sets of simulations. One, a small domain simulation at 3 different fixed SSTs, which takes the form of a 100 kilometer square for our explicit models, either with 1 kilometer resolution for the cloud resolving models or 200 meter for LESs. The models with parameterized convection do this as a single column simulation. We also then have a large domain set of simulations, which is the global domain for GCMs and GCRMs, which the latter are run on reduced Earth radii, or a 6,000 by 400 kilometer rectangle with 3 kilometer grid spacing for the cloud resolving models. We also have a suite of WRF simulations, which run using GCM-like resolution and column physics, but on the rectangular domain. And so turning first to our RCE state, we find that there's actually quite a widespread in this representation of the RCE state in this ensemble of models. So shown here are domain average temperature profiles, where the black line is the ensemble mean across all the models, the blue shading the spread, and the full range, and then the orange lines show the interquartile range. The temperature profiles are close to, but systematically cooler than a moist adiabat. But despite their common appearance on this plot, at a given height, the spread in temperatures is actually up to 10 Kelvin, which is quite a large discrepancy. Similarly, we see that there are quite wide differences in the relative humidity profiles simulated with these models. In the small domain simulations, which is the top panel, we see a spread of relative humidity between 25 and 90% in the mid-troposphere. In the bottom panel, our large domain simulation has a bit more of a consistent shape and better model agreement, but still a large spread. It then makes sense that we also see quite a large spread in the cloudiness in these simulations, especially in our small domain simulations where cloud fraction, which is diagnosed either from a cloud scheme if the model has it, or a threshold value of cloud condensate, can vary from very small amounts of high clouds to actually domain filled with very thin high clouds. We see this large spread as well in the large domain simulations and in our total water, cloud water as well, which is simply the sum of the cloud liquid water and cloud ice. However, one thing that we don't find are any consistent differences between the parameterized and explicit models. The cloud resolving models disagree with each other just as much as the GCMs do. But where the models exhibit better agreement is how things respond to warming. And so across the majority of models, we find that Our high clouds, our anvil clouds, rise in height at an average rate of about 0.3 kilometer per Kelvin. They warm slightly in accordance with the proportionally higher anvil temperature hypothesis, with an average increase of 0.4 Kelvin of the anvil temperature per degree of SST warming. And we find that in 70% of the models, we have a decrease in our anvil cloud fraction with warming, consistent with some previous literature, but this confirms, that in more detail. Turning now to self-aggregation, if we consider our two different types of domains, we find that nearly all of our small domain simulations are unaggregated, whereas nearly all the large domain simulations, which are the ones shown here, are aggregated. So we have our cloud resolving models on the left, our GCMs, and our global cloud resolving models on the right. And there's quite a spectrum here in the structure, the size of the deep convection, outgoing longer radiation is plotted here. But again, there are areas where there are robust results and models agree. And in particular, models agree on how this aggregation impacts the mean state. And so if we can compare pairs of large and small domain simulations for each model to understand the impact of aggregation. And looking at the average profiles for the large versus small domains, we find that with aggregation, there are robustly fewer high clouds. There is a drier atmosphere, both in terms of relative humidity at individual levels, as well as an integrated metric such as precipitable water. As we go from small to large, we have a decrease in that quantity. We also find that the aggregated simulations are warmer, and then consistent with that, have a more stable lapse rate. We additionally find that the large aggregated simulations have more rainfall, consistent with greater atmospheric radiative cooling in the more aggregated simulations, and they have more cooling to space, and so they have less net incoming radiation at the top of the atmosphere, meaning more cooling to space. In order to assess more quantitatively the degree of aggregation, we use three different metrics. The first is substance fraction, which indicates the fractional area of the domain covered by sinking air, and that's larger if you're aggregated or more aggregated. We also use IORG, which is a clustering metric that compares the nearest neighbor distribution of convective entities to the theoretical expectation from a random distribution. And if IORG is greater than 0.5, that indicates clustered convection, and the larger it is, the more clustered it is. We also consider the spatial variance of column relative humidity, which reflects the clear signature at aggregation in broadening the humidity distribution. Using these three metrics across all our models, we find that here in the simulations at 300 Kelvin, there is a very wide spread in the degree of aggregation, with some models being strongly aggregated and some models barely aggregated at all. Looking at our three different metrics, they each exhibit wide spreads, but we do find that they are correlated with each other. Across all models, substance fraction and IORG are weakly correlated, but if we consider the cloud resolving models and GCMs separately, we see better agreement. So in the cloud resolving models, there are very high correlation coefficients between all different pairs of metrics, meaning that if, say, one metric says that a model is strongly aggregated, the other metrics will agree, at least in a qualitative sense. In the GCMs, IORG and substance fraction are also correlated, though not so much with the variance of humidity, though we notice that there's kind of a group of models that are a bit of an outlier. Those are those WRF models on the sort of strange rectangular domain. And so if we ignore those, we see a more consistent relationship as well. We can then quantify how aggregation is changing with warming by plotting the rate of change of these different metrics over our three simulations at different SSTs. And we find that there's really no consensus on how aggregation changes with warming. Half the simulations have an increase with warming and half have a decrease, and that's true really regardless of which metric you look at. We do notice, though, that the GCMs on the right-hand side of the plot tend to have more of an increase in aggregation with warming than our cloud resolving models do, and that will turn out to be important later on. Now, we've shown here that self-aggregation impacts the climate, and so it's reasonable to ask, does it impact climate sensitivity? But first, we need to know what is the climate sensitivity in the RCE MIP simulations. Since these are simulations at fixed SST, we can calculate the SES-type net climate feedback parameter by looking at the rate of change of the net top of atmosphere radiative fluxes. That can be then converted into a rough estimate of equilibrium climate sensitivity using a typical value of radiative forcing from doubling CO2. We find that in our small domain simulations that are unaggregated, they would tend to have the equivalent of a high climate sensitivity, though again, remember that these models are really only having tropical deep convection, not other sort of climate regimes in them. We notice, though, that there's actually pretty good agreement between our highest resolution models, the LES models, and their coarser resolution counterparts. And so that's interesting to see. When we go, however, to our large domain cloud resolving model simulations, we see that the spread in climate sensitivities is significantly larger, including even a few that have positive feedback parameters, which would indicate an unstable climate. This spread increases even more if we consider our parameterized models, the GCMs, which have a huge spread and on average lower values of climate sensitivity compared to the models with explicit convection. So given that we have a widespread in climate sensitivity, a widespread in self-aggregation, a widespread in the changes in self-aggregation with warming, that begs the question, does the intermodal spread in self-aggregation explain the intermodal spread in climate sensitivity? We find that in 70% of the RCE MIP models, though heavily weighted towards the GCMs, aggregated simulations have a more negative climate feedback corresponding to lower climate sensitivity than their unaggregated counterparts. However, it turns out that there's no correlation across models between the average amount of aggregation and the climate sensitivity. Instead, there is, though, a relationship between the changes in aggregation with warming and the climate sensitivity. And so what's shown here is the climate feedback parameter for all of our models, blue in the cloud resolving models and red are the GCMs, against the change in IORG, one of our aggregation metrics with warming. And so for the models that have an increase in IORG that become more aggregated with warming, those tend to have the more negative feedback parameters or lower climate sensitivities. Models that have decreases in aggregation with warming tend to have the smaller feedback parameters or higher climate sensitivities. And we also note that the red models, the GCMs, on average have lower climate sensitivities, more negative feedbacks, because the GCMs on average have more of an increase in aggregation with warming, whereas the cloud resolving models, their kind of average change in aggregation is 0. We also found that this response is mostly due to the enhanced clear sky outgoing longer radiation due to mid-tropospheric drying in a more aggregated state. So to summarize, this set of coordinated intercomparison of RCE simulation really offers great opportunities for us to investigate lots of different questions related to tropical climate. But we found that the RCE state in terms of the temperature, humidity, and cloudiness varies substantially across our models, which is maybe surprising that it varies that much, though one has to remember that RCE is fairly unconstrained, which makes it a very tough test actually for these models. And so it really exposes, I think, what the true spread in these representations of convection actually are, things that might be masked over by stronger constraints in other types of configurations. We do see some model agreement, though, in particular when it comes to changes in clouds with warming, the anvil clouds rise and slightly warm, and in 70% of models decrease in extent with SST warming. When it comes to self-aggregation, nearly all models aggregate to some extent in the large domain, but there's a wide variability in its structure and degree. There's no consensus on how the degree of aggregation changes with warming, but models do agree on its impact on the mean climate. When it comes to climate sensitivity, the large spread in climate sensitivity can be explained by the large spread in changes in aggregation with warming, in addition to contributions from changes in shallow clouds. And I'd like to end by just noting that the RCEMIP data is now publicly available thanks to the DKRZ, and everyone is able to download it. And I really encourage you to do so to make use of this unique data set. And also to please consider submitting a paper to our special collection across AGU journals led by James. And all papers using radiative convective equilibrium are encouraged. It doesn't have to be limited to RCE. And if you have any questions, please feel free to get in touch or visit our website or our 2 papers that were recently published in James. Thank you very much.